which is on normalized frequency of an optical fiber here. So these are the learning outcomes. At end of this session, students will be able to describe the normalized frequency in optical communication. So before starting to this normalized frequency of an optical fiber here, just recall which are the types of rays, how it get propagated in the optical fiber here. Because so we need to understand what is the skew rays, meridional rays and the axial rays here. So the skew rays which does not passes through the center of the core and which never touch to the center of the core here. So it will be bound near the boundaries of the core here. So that is known as in the skew rays here. And the meridional rays which is cut by the central of an core here, that is known as the meridional rays here. And the axial rays is known as the rays which passes through the center of the core here. So by this we can send the rays, either a skew rays or meridional rays or the axial rays here. So when you are going to incident the light on the optical fiber, that is known as a numerical aperture here. Okay, so on acceptance cones, at which angle you are going to incident, so that there will be a maximum gathering of an light inside the fiber optical here. So depending on that, we need to calculate the normalized frequency of an optical fiber here. So which is most important parameters, that is known as a V number, is called as a normalized frequency. It is an unitless calculation. So it is expressed as an V is equals to 2 pi A upon lambda into NA here. Okay, so that is known as an the NA, that is the numerical aperture. A is the radius of the core and lambda is nothing but it is the wavelength of an light here. Okay, so so it signifies the V number, that number of modes propagated in the fiber here. So when V is less than 2.405, the fiber can support only one mode, and that is known as a single mode fiber here, SMF here. But when V is greater than equals to 2.4, that is the fiber can support many modes. It is known as a multi-mode fiber here. And V is equals to 2.4 means it's corresponding to the cutoff wavelength here. So there are two fibers are there. One is the single mode fiber and second one is your multi-mode fiber here. In the single mode fiber is used for the longer distance communication when only one mode is propagated along the distance here. So whenever you want to send the data at a longer distance, the single mode fiber is used here. And the multi-mode fibers are used in the LAN communication where the smaller distance are there, like this here. Okay, so that is the multi-mode fiber here. So it can be a step indexed or the graded index. Step index means what? The core is having the uniform refractive index, and step index, that is the cladding, will have the different refractive index here. In graded index, what happens? The Ri, that is the refractive index in the center of the core, will be maximum. As we move out from the center to the cladding, it becomes very less here. So the refractive index is going to be changed here. So your velocity of light changes in the graded index when it going to travel inside the fiber optical here. So that consists of in the normalized frequency here. So we'll understand the V by using this example here. So we'll switch on to the demo part now. So we need to calculate that how many modes are going to be transmitted and how many modes are going to be supported in the fiber here. Okay. See, as this is the step index here. So as we have discussed now, there are the step index and the graded index here. A step index is same here. The Ri of this core is same here. But in graded index, so this is the graded index. So in which this will have the maximum of Ri, and here it will be less here. Okay, so it will be N1 and N2. This is N2 and this will be N1 here. Okay, so here as a core radius of 8 micron here is core 8 micron here, that is nothing but A, which is 8 micron here. Okay, and core and cladding indices are, that say N1 is equals to 1.458 and N2 which is given 1.44 here respectively. So what is the V number of fiber is operating wavelength at 1300 nanometer here, 1300 nanometer here. So we need to calculate this, how many, what is the V number here, and in second statement what they have asked, that how many modes will be supported in this fiber here. So number of modes we need to calculate and V number, and if it is operated in single mode and at 1500 nanometers with a given indices, means Ri with the same indices. So what will be the radius now? Because as we know that in single mode fiber it is up to 2 to 6 micron meter, and for multi mode it is up to 10, 25, 85 and 125 micrometers of diameter will be there here. Okay, so now we'll calculate here. So as we have seen in the previous slide, that is V is calculated by 2 pi A upon lambda into N1 square minus N2 square here. So now substitute the values which are there. Lambda is given 1300 into 8 micron, means 10 raised to minus 6 here. Okay, into, that is N1 is what here, 1.458 square minus 1.4 square here. Okay, so if you solve this all the things, so what will happen, you will be getting 8.83. V is unitless here, so your normalized frequency comes to be, and V is equals to 8.83 here. Okay, so now what they have told you, how many modes will be supported here. So for that, total modes, okay, supported. So how it is calculated? It is calculated V square by 2, that is M. Okay, for the single mode here. Okay, V square by 2 here. So 8.83 upon 2 square is equals to, it comes to be an 39 here. Okay, it comes to be an 39 here. So number of modes, okay, number of modes will be 39 here, and V will be 8.83. Okay, so now what they have asked you, if a fiber must operated at a single mode fiber at a 1500 nanometers here, so with a indices as given, so what must be radius of the fiber here. So if you see how to calculate an radius now, because we have to make use of this same formula, and we know that we need to calculate this A here. So how much value of V you are going to take, how much value of V are going to take, as we have seen in the previous thing, that if V is equals to 2.405, it will be the cutoff frequency. If it is less than, it supports the single mode. If it is greater than, it supports the multi mode here. So for that, so if a fiber must be operated at a single mode fiber, then A is equals to, we need to put the value. So for directly, if I shown here, so we can use this formula, that is 2 pi A upon lambda N1 square minus N2 square here. Okay, so A, we have taken A from this, and V we need to take, because it is a single mode, it is 2.40 into lambda, that is N1 square minus N2 square here. Okay, so substituting the values, that is 2.40 into 1500 nanometers here, it is nanometer here, upon same indices 1.48 square minus 1.44 square here. Okay, so when you calculate this, so you got 2.5 micrometer here radius. So as we have discussed in the single mode diameter, how much it will be, it is maximum you are going to have 2 to 6 micrometer here. So what happens, the fiber should not have the radius longer than 2.5 micrometer for a single mode operation at 1500 nanometers here. So the operating wavelength, that is the given as in 1500 nanometers, so it should be 2.5 micrometer here. Okay, so I hope this you have understood. Okay, so the fiber should not have the radius larger than 2.5 micrometers for a single mode operations at 1500 nanometers here. Okay, so these are my references. Thank you.